Hey guys, Mr. Kyle, Myers Mathematics, and let's just jump right into it. So last week, if you didn't see the post, it was on just regular limits, just the basics of limits, the basic steps, and so it looked something like this, but more explained in detail. So step one, plug it in, because you never know. You could just be able to plug it in. Step two, if it doesn't work, try factoring. If that doesn't work, try conjugates. If that doesn't work, try something called L'Hopital's rule. And then if none of that works, then there maybe isn't a limit. So, but what if you have infinite limits though? So what if the limit is to infinity and beyond? To infinity and beyond. So, for instance, let's say I have the limit as x approaches infinity of 1 over x. Well, actually, this whole thing, all of infinite limits, really just revolves around step 1 of basic limits. Right? You're not going to try factoring, conjugates, all that kind of stuff. None of that stuff is really going to matter that much with infinite limits, but you can plug it in. You can plug in infinity. So here's what you would do. You would just say, okay, 1 over infinity. But then I guess your question next would be, what is 1 over infinity? So then we have to say, okay, well, what does that mean? So if I say 1 over 0.5, right? If you were to type that into a calculator, it'd give you a really small number. It would give you 2. Just give you 2. If I said, let's use fractions. It'll make more sense if I use fractions. So if I, or actually, let me use just bigger and bigger numbers here. So 1 over 1, that's just 1. If I do 1 over 10, that's 0.1, right? Or how about 1 over 100? That's 0.01. And then you kind of notice a pattern, right? Every time I add a 0 to 1 over a really big number, my decimal gets really, really small. So it basically gets to where it's going to go out a million zeros. The zeros are going to go to infinity and beyond, never really reaching the point where you can add a 1 to that decimal. And so it's 0. So 1 over infinity is just 0. And that's really important to understand infinite limits, because if the bottom is bigger, if the bottom is going to infinity faster, this is the whole idea behind infinite limits. So I'll write this out. So basically, if the denominator is going to infinity faster, so I'll put that in caps, faster than the numerator, you will have 0 as an answer. If the denominator is going to infinity faster than the numerator, you'll have 0 as an answer. That's the whole idea here. So let's look at a couple different graphs. If I did 1 over x, y equals 1 over x, it looks kind of like this. And then you got a graph like that and a graph like that. So as x is approaching infinity, it's going to 0. As it's approaching negative infinity, it's also going to 0. If I did the graph of let's say, just y equals x. Let's just do y equals x. That's just going to be a line going through the middle. So that would be just kind of going to infinity. I mean, it's going up as x gets bigger, y gets bigger. So that's the idea, is how fast is it going now, versus if I said y equals x squared, right? Now we have a parabola. That's going to infinity faster. As x gets bigger, y goes to infinity faster. It has a bigger slope. That's the whole idea of faster here. So the slope is bigger as I go up. Or, even better, what if I have y 2 to the x? That's exponential. So then that's going to go even faster. It's going to skyrocket. That's going to infinity much faster than an x squared function, or x cubed, or x to the fourth, or any power of x. So some functions go to infinity faster than others, and here's what I'll do. I'm going to give you the list of all the different functions you might run into and how fast they go to infinity. Kind of rank them here. So let's start with really slow. So a really slow function might be something like y equals a number. So for example, y equals 2, because it's not moving. It's not going to infinity at all. Right? So that would be a really, really slow function. Also, sine and cosine. Sine and cosine, because they're just waves. Right? They're not really going anywhere. They're kind of just oscillating between -1 and 1, unless you do some sort of transformation to them. So those are not really going anywhere. Then, let's use maybe some orange. So then you have a graph that maybe is kind of going somewhere. Let's say a logarithm. So a logarithm. Because that graph is basically the reverse of an exponential. It is going to go somewhere. It's going to go to infinity, but as x is going to go to infinity, y is just barely going to get a little bigger as you go. So it's just barely, as it goes to infinity, the slope is just barely increasing, just barely. Then next we would have, let's see, I'm trying to remember my color wheel right now. Red, and then orange, and then yellow. There we go. Whew, goodness gracious. Okay, so yellow, use a pencil here. You'd have maybe a line. So y equals x. It's just a line. So it's just going to, go to infinity like that. And there you go. It's, it's going to infinity. It's good. It's getting there. Slow and steady wins the race kind of thing. But it's not too fast yet. And then we would have, we'd start to get to green functions. So green functions might be like y equals x squared, and then x cubed, and then x to the fourth, right? I'll just put a plus on there because you get the idea. So as you increase the power of x, it's going to go to infinity faster. And so, it'll be faster as it goes to infinity. And then, kind of the last step, the last leg of the race here would be the exponentials. So exponential. Right, so for instance, if I have, and I'll do a little graph here like I did for the logarithm, but I kind of already drew it earlier, but it looks something like that, right? It's going to go to infinity. So for instance, for the logarithm, I could say log base 2 of x equals y, might be an example. And then for the exponential, it would be something like y equals 2 to the x. All right, so it's just something like that. All right, so there might be one that I missed. If there was, let me know in the comments below. But you just have, regular lines, and then before that you have, a couple other things that go a little slower than lines. But basically a line is like the middle ground. And then you have, different powers of x and exponential functions and that sort of thing. Actually, one thing I didn't include in this list was square root functions. Square root functions are going to go a little faster than logarithms, but not quite as fast as a line, because square root functions are going to slow down as they go to infinity. So actually we could probably squeeze those in right here. So square root functions. Square root of x would go faster than the cube root of x, right? because it's kind of the inverse. It's kind of the opposite of x squared and x cubed and that sort of thing. So here's what this looks like. Sorry, let's say I have sine of x over x. So the limit as x approaches infinity. Well, x goes faster. X is a line, so that's my yellow one here. And it goes faster to infinity than sine does. So should get 0. And you can also plug in infinity if you really wanted to, but I mean, that's what's happening, right? So the bottom is going faster. Or let's say I did the limit as x goes to infinity of x over 2 to the x, right? So 2 to the x is going to go way faster to infinity than just a regular old line would. So it equals 0, right? Now, the other thing that happens with infinite limits is if you have the same thing on the top and the bottom. If you have the same thing on the top and the bottom, then it's going to approach something else besides 0. So for instance, let's say I have a polynomial, right? So actually, let me change this color back to red. So let's say I have a polynomial, and I have 3x squared plus 1 over 2x squared minus 7. Okay, if the degrees are the same in a polynomial, or if it's going to infinity just as fast, so we go up here, if the denominator is going to infinity faster than the numerator, you have 0. But if they're going at the same rate, basically you can just take the first numbers you see, and that would be the answer, right? So if this is f of x, and I want to know the limit as x approaches infinity of that function, then it's just the first numbers. You just take the first numbers, divide those, and then there you go. There's your limit as you go to infinity. And all of this stems from when you had to learn about horizontal asymptotes. So if you remember back to horizontal asymptotes, it's exactly the same thing. Wherever the horizontal asymptote is, that's where it's going to approach as it goes to infinity. Now, if none of this works, if it's going to infinity faster on the top, or if you don't have a bottom function at all, it's just, 1, because you can write anything over 1, then you don't have a limit. It's got to be approaching something, so you've got to have either the same amount of x's, same type of x's on the top and bottom of a fraction, or the bottom has to be going faster, in which case it would be 0. All right, so that's it for today. I hope that video was helpful. If it was, give it a like. If you want to see more videos like this, go ahead and hit subscribe, and then receive notifications and all that good stuff. But on my website, myersmathematics.com, I have a kind of a PDF guide, which is just the 5 math mistakes that everyone makes and how to avoid them. Literally, that's just the title, and it's there for free. What it does is it kind of explains like why everyone misses certain things and breaks it down into 5 categories. There's only really 5 reasons why people miss math problems. So you can download that on my website for free at myersmathematics.com, and I hope to see you in a future episode.